In 5, 4, 3, 2, 1, launch. Smoke, fire.
Hi, I'm Jake Gamble. I'm with Lamar's rocketry team. We are a senior design team we created in order to help create a foundation here at Lamar for future engineers who are interested in aerospace. As you can see back here, we've created not one, not two, but three separate rockets. We had to start small before we could go big. And so I'm just going to give you a brief overview of the processes and steps we took along the way. So to start the project, before we even began, we had a rocket already pre-manufactured. We had some of the basics down, which you can see here. It's still being worked on. We're preparing it for the symposium, but before we could even launch this, we actually had to take a step back and go over the rules and regulations that the FAA requires to even launch some of this stuff. So technically, this rocket here was too big to even launch. So we had to take a step back and fly an even smaller rocket, which you can't see here, but is actually generally scaled to this one right here. We ended up losing that rocket because it went far higher than we expected, and so we ended up going with our other manufactured rocket for our second flight. This rocket here weighs about 5 pounds, is about 6 foot tall, and flew about 4,500 feet in the air. And this was actually our second successful flight. And so after we flew this one, we began preparing for our final design, which you can see here. So to begin designing a rocket, one has to set parameters. These parameters are usually set by either a competition or your own. So usually one of these parameters is a general height or velocity margin that you want to be in. And so once these parameters are set, you can begin the iterative process of designing the actual rocket. It can be a bit daunting, but if you break it down piece by piece, it actually doesn't take too long. So if we begin, we open a Roxen file and just create a very general assembly. We can then insert different motors and see different altitudes and test different configurations to get to where we approximate our goal. Once that is complete, we can begin the actual engineering analysis to make sure everything's structurally intact. Okay, and so to start this process, we start with a CFD analysis. We have been using this using ANSYS Fluent. So with our simulation model, we can find our maximum velocity or any velocity profile that our rocket wanted to go. And with that data, we can import this into ANSYS Fluent to figure out the aerodynamic stresses and pressures, temperatures, all that may vary throughout our flight. And so once this is configured, we can then import those stresses and pressures into a finite element analysis that we've been using with SolidWorks in order to figure out the stress and strain that the rocket may undergo. And then from here, we can verify with our selected material that the rocket will or will not fail throughout flight. So this here is our final senior design rocket. So what you see in the back were our first two rockets, and you actually can't go big until you fly small. And so what's actually good about this is conceptually it's not too much different than these smaller rockets, but given the larger scale of it, there do come different complexities. And so I'll just kind of start back here. Back here is where our first motor goes in. You want the larger motor typically to be at the end, given the mass is discarded. And so we opted for fiberglass fins just to add strength, given this is a high failure point. And then we move up through the rocket. You have a parachute that comes out in here. And then this is probably the most complex part of the rocket. This here is where the igniter will go off to stage the second motor, which will be up here. It's done by programming a small piece of electronic just based off time and velocity. And so once that point is reached, this motor ejects, separating the two stages, and will go off. It's a rather long burning motor, so we actually opted for that given the lower velocity profile just to make sure our rockets stay safe. And then so we move up through here. This is where probably the most expensive part of the rocket is. There's probably about $500 worth of electronics in here. You got a GPS, you got 2 separate altimeters, which both deploy these 2 ends right here, where a small parachute deploys first at apogee, and then our bigger parachute deploys at around 1,000 feet, just to ensure a safe descent. And so one of the complexities we actually had coming in with this was running our CFD analysis. And so given this is a 2-stage rocket, there's actually 2 different CFD simulations we have to run, once for the first stage, once for the second stage. And so basically we're designing around 2 rockets in one. And so given this level of complexity, we opted for a different material. Space grade proprietary composite. It's actually used in old tank ammunition. So this is the material we selected based off our CFD and FAA results to ensure a structurally sound rocket. So with this final rocket, we hope to launch here around April 22nd. And with that final launch, we hope to lay the groundwork for not 1, not 2, but many generations of students and engineers here at Lamar University. With that, we have not only secured 6 times the funds that we attained for this semester, but we've also found about 20 to 25 club students, and a senior design team for next year. And so what sets us apart as far as the senior design is not only did we build, manufacture, and fly what we set out to do, but we've created much more for the years to come.